We have to discuss on theorems on geometric series. On geometric series, we have lemma. The first one is if a series summation n is equal to 0 to infinity un is convergent, then limit of un as n tends to infinity is equal to 0. Okay, now we have to see proof of this theorem. Here let Sn denote sequence of nth partial sum of the series summation n is equal to 1 to infinity un, then summation n is equal to 1 to infinity un is convergent. So that implies the sequence Sn is also convergent. Next, that implies limit of Sn as n tends to infinity is equal to L. So that this means if the sequence Sn is convergent, that means limit of Sn as n tends to infinity is equal to L. So then limit of Sn minus 1 as n tends to infinity is equal to L. Now un is equal to u1 plus u2 plus u3 plus up to plus un minus u1 plus u2 plus up to un minus 1. So next, that is un is equal to, so first one, this can be written as Sn, and this one is Sn minus 1. So next, so apply the limit on both sides. So we get limit of un as n tends to infinity is equal to limit of Sn as n tends to infinity minus limit of Sn minus 1 as n tends to infinity is equal to, so the limit of Sn as n tends to infinity value is L, that is finite, minus limit of Sn minus 1 as n tends to infinity, this is also is equal to L. So L minus L is equal to 0. So that means if summation n is equal to 1 to infinity un convergent, then limit of un as n tends to infinity is equal to 0. Here we have one note. The convergence of the above lemma is not always true. That is, the nth term may tend to 0 as n tends to infinity, even if the series is not convergent. For example, the series summation n is equal to 1 to infinity un is equal to summation n is equal to 1 to infinity 1 by root n. So apply limit on both sides. So we get limit of un as n tends to infinity is equal to limit of 1 by root n as n tends to infinity. So when we apply the limit n tends to infinity, we get 1 by infinity. 1 by infinity is 0. Next, now consider Sn is equal to 1 plus 1 by root n, 1 plus 1 by root n up to plus 1 by root n. So here Sn greater than 1 by root n plus 1 by root n up to plus 1 by root n. So its nth term is n by root n, that is equal to root n. So apply the limit on both sides. limit of Sn as n tends to infinity is equal to limit of root n as n tends to infinity, that is equal to infinity. So therefore the sequence Sn of nth partial sum diverges to infinity. Hence the series summation n is equal to 1 to infinity un diverges to infinity. From the above lemma, we have the following observation. The first one is summation n is equal to 1 to infinity un is convergent, then limit of un as n tends to infinity is equal to 0. And the second result is limit of un as n tends to infinity is equal to 0, that implies summation n is equal to 1 to infinity un may or may not be convergent. And the third one is limit of un as n tends to infinity not is equal to 0, then summation n is equal to 1 to infinity un is not convergent. Next, second lemma. A series of positive terms either converges or diverges to plus infinity. So proof, let summation n is equal to 0 to infinity un be a series of positive terms and Sn be the nth partial sum. Then Sn plus 1 is equal to u1 plus u2 up to un plus plus 1. So that means Sn plus 1 is equal to, so this is Sn plus un plus 1. That implies, so in this step here we taken Sn inside, so that implies Sn plus 1 minus Sn is equal to un plus 1, that is greater than 0. So next Sn plus 1 greater than Sn for all n. So that means this is what that implies sequence Sn is monotonically increasing sequence. So now there are two cases here. There are two cases arises, that is the sequences may be bounded or unbounded. Case 1. When Sn is bounded, since Sn is monotonically increasing and bounded from above, so it is convergent. So already we have theorem, so that implies the series summation n is equal to 1 to infinity un is convergent. Then we have case 2, when Sn is not bounded above. So since Sn is monotonically increasing and not bounded above, so it is divergent to infinity. So that implies the series summation n is equal to 1 to infinity un is divergent to plus infinity. So revision, here in this session we have to discuss on lemmas on the geometric series. So these are reference books, refer for this session. So thank you very much.